In this video, we will be looking at different scenarios that can be modeled by periodic functions. And for the periodic functions, we will be focusing on sine and cos. But before we get into our first word problem, we're going to refresh on the general equation for sine and cos. So just a reminder, your A value is the amplitude, and the amplitude can be found by taking your max and min and subtracting them and then dividing by 2, and it will be the absolute value for the actual amplitude. Whether it's a positive A or a negative A value will depend on if you have a positive sine or cos, and that's based on your starting point that you choose. Next, we have our K value, and that can be found once you've determined the period. If you do 360 divided by the period, you will get the K value. The phase shift or the D value depends on the starting point that you pick. It will either be on the midline, meaning it's a sine function, or the max or min, meaning it's a cosine function. And finally, C is that central axis or your midline, and that can be found by adding the max and mins and then dividing by 2. So let's get started with our first example. A carnival Ferris wheel with a radius of 7 meters makes one complete revolution every 16 seconds. So the radius of 7 meters seems important, and one revolution, so one complete cycle, takes 16 seconds. That should already make you think of the period, the length of one cycle. The bottom of the wheel is 1.5 meters above the ground because obviously someone can't get on at ground level or else the Ferris wheel would be scraping the ground. All right, so for A, we're going to draw a graph to show how a person's height above the ground varies with time for 3 revolutions, starting when the person gets onto the Ferris wheel at its lowest point. So first thing I'm going to do is draw the Ferris wheel to get a sketch, and then I'll think about my actual sinusoidal graph. So here's the Ferris wheel, and here's the ground. We know that the bottom of the Ferris wheel is 1.5 meters above the ground, which means that is going to be our minimum point because that's the lowest height that a person can be at. So that's our minimum. We know that the radius of the Ferris wheel is 7 meters. From the center of the wheel to the bottom is 7 meters, and then to the top also 7 meters. So the halfway distance, or our midline, is going to be 7 meters above the 1.5. So 8.5 meters above the ground will be our midline. And then if we add another 7 meters just to get to the maximum height, that will be 15.5 meters. So I'm just adding the radius to the 1.5 2 times to get my midline and my max. So now that I have those 3 key lines, I can start a sketch for myself. So that will be our height. So I will put the height in meters, and it's important that we label our scale. And then for our x-axis, we are talking about the number of seconds. So I'll put time in seconds. Now, when I label my scale, it doesn't have to be perfect, but I have to make sure I include the 1.5, 8.5, and 15.5. So just roughly, I don't want to be completely off with my scale, but it doesn't have to be perfect either. So there we are. I've labeled my key lines, and I'll even highlight them just to give me a guide. Next, for my time scale, I know that one complete revolution is 16 seconds. So that means that the period is 16, but I need 3 revolutions for my sketch. So when I do my scale, I'll make sure I have 16 seconds for one cycle, and then add on another 16 to get to 32, and add on another 16 to get to 48. So now I can start plotting points to represent a person's height. on the Ferris wheel. So they're starting at the lowest point, and then they're going to head upwards towards the midline and max, and then come back down. And all of that has to occur in 16 seconds. So at the end of 16 seconds, they will be back down at that minimum height. Now, if we remember, we know that the period of a sinusoidal function can be split into fourths for when every key point occurs. So if I take that 16 and divide it by 4, I get 4. So every 4 seconds, I will be on my new line. So then I can split off my scale into quarters so that I have 4, 8, 12, and 16. So at 4 seconds, we'll be at 8.5. At 8, I will be at the maximum. At 12, at the midline, and then I'm back at my minimum for that full cycle. And then I'll continue to fill in the rest of my scale every 4 seconds. So 20, 24, 28, 36, 40, and 44. Just adding 4 from that key point. And now I'll continue plotting my points, and then I'll connect the dots to get my 3 rotations. And there we are. So now we have our sketch. Now we can do part B, where we want to find an equation for this graph. Now I can see my midline already. So my midline is 8.5. My amplitude is actually that radius of 7, but if you can't see it from the graph, we can just do the calculation where we take our maximum, subtract our minimum, and divide by 2. So 15.5 minus 1.5 is 14, and 14 divided by 2 is 7. For my k value, I can just take 360 and divide it by the period, which is 16. And if I just reduce my fraction, it would be 45 over 2, or you can write it as 22.5 as well, and that's perfectly fine. So now I have most of my information. I just have to pick my starting point to figure out if I will have a phase shift and if it's going to be sine or cos. So I'm going to pick that initial start at the minimum as my starting point. And if I use this as my start, then we have a negative cos function because we're starting at the minimum with no phase shift. And I like to avoid the phase shifts if I can. So now, before I start writing my equation, I need to write some let statements so that we know what our variables are. So I'm going to have h for height. So let h represent height, and it's in meters. And let t represent time in seconds. So now I can use my function notation and have h at t equals, so my amplitude is 7, but I mentioned it was going to be a negative cos function. So negative 7 cos. My k value is 22.5, and I don't have a phase shift because I avoided it based on my strategic starting point that I chose. So we're just going to have 22.5 t, and then let's put our midline, and it's at positive 8.5. So there is our equation to represent this scenario. And now you can do various things with this equation if you wanted to. I can ask you the height at various times, and you can just replace t with whatever time and plug it into your calculator, making sure you're in degree mode. Or I can even give you the height, and then you have to solve this trig equation. And we'll practice that in a different scenario. But notice, once you took the words and created a sketch, finding the equation of the function is something you've done before. Okay, our next scenario. The Bay of Fundy, which is between New Brunswick and Nova Scotia, has the highest tides in the world. During low tide, there is no water on the shore at all, while at high tide, the water covers the shore with a depth of 16 meters. So right there, we already have our max and min. The min is 0 meters and the maximum is 16. High tide occurs roughly 12 hours after low tide. So before I go to A or B, I just want to translate these words into some information. So our max is 16 meters, our min is 0 meters, which tells us our midline as well, because for midline, I'm just going to add 0 and 16 and divide by 2 to get 8. And I can also get my amplitude from here, where I take my max minus min and divide it by 2, and I also get 8. And now I want to figure out what this 12 hours represents. So if I'm going from my high tide to my low tide, and it takes 12 hours, that means we only have half a cycle, because a full cycle would take me back to the maximum. So 12 hours equals half the period, which means a full period will be double 12, which is 24 hours. So now, because I'm already at the period, automatically I can get the K value. So why not do that? 360 divided by 24 is 15. So I already have a lot of really good information here just from deciphering those words. So now let's go ahead and read what part A says. Assuming the first low tide occurs at 8 a.m., model the depth of water D in meters with relation to time T in hours for 1 day. All right, so let's go ahead and get a sketch going. And I know I'm going to have time in hours on my x-axis, and I'm going to have the depth in meters on my y-axis. And now I can label a few things. So I know my minimum is going to be at 0. I know my maximum is 16, and I will also label my midline. And while I do that, I will just highlight those lines just to make it easier for me when I'm drawing my key points. Now for my scale, I know that the period's 24 and we are dealing with a 24-hour clock here, so I do want to make sure I go to at least 24. But before I decide on that, I am just going to go to part B and see what they're going to want from me. If you want to take a canoe ride, the tides must be at least 8 meters high. At what times can you go canoeing if you're in the area for 2 days? So I see that word 2 days, so maybe I do want to complete 2 cycles here and include 48 hours instead of just 24, so I have a better visual for part B as well. So I will put 24 here and 48 here. And on my scale, I know I'm going to need more information or more markings because I know that the first low tide occurs at 8 a.m. So I do need to divide this a little better to have more accuracy. So I am just going to go up by 4s. So 4, 8, 12, 16, 20, 24. And then again, I'll break this up into 6 pieces here. And then from 24, I will go to 28, 32, 36, 40, 44, and then 48. And now we can start sketching. So I know my low tide occurs at 8 a.m. So 8 a.m. would be a minimum. And now with my period, I'm going to get my key point. So my key point is a quarter of the way. So 24 divided into 4s is 6. So every key point occurs 6 hours apart. So from 8, if I add on 6 hours here, then I will be at 14. So halfway between 12 and 16. And then from 14, if I add on another 6, I'll be at 20. Add on another 6, I'll be at 26. Add on another 6, I'll be at 32. And then I can also go in the other direction as well, just to make sure I start from hour 0. So from 8, if I subtract 6 at 2 hours or at 2 a.m., I will be at that midline. And then I'll continue in the other direction as well. So right now I'm at 32, add 6 and I will be at 38. Add another 6, I'll be at 44. And then add another 6 and we'll be at 50, which is past the 2-day mark, but we can just continue anyway. And then I'll just extend it to the 0 as well. And there we are. Now we have our sketch, and now we can write our actual equation. So they did give us d for depth and t for time. So then I have d at t equals, and for my starting point, I'm just going to use the closest key point that's on the max, min, or midline. So I'm just going to use the point at the midline, and that's at 2 hours. So that coordinate is 2, 8, and it is heading downwards, which means we have a negative sign here. So I'm going to have negative, and then my amplitude is 8. I chose sine. My k value is 15, and I do have a phase shift 2 hours to the right. So I will have t minus 2, and then plus 8 for the midline or central axis. So there we are. That is the equation. Now that we have the nice sketch and we have an equation to model the scenario, we can go to part B. So in part B, it says, if you want to take a canoe ride, the tides must be at least 8 meters high. At what times can you go canoeing if you're in the area for 2 days? So that 8 meters, what's really nice about it is that that is our midline, and we have the exact times for our midlines. We have 2, we have 14, we have 26, we have 38, and 50. And now I'm just going to highlight the parts where the tide is above 8. So the very start is above 8 from 0 hours to 2 hours, so from midnight to 2 a.m. And then from 2 a.m. until 14 hours, which is 2 p.m. if you think about the 24-hour clock, it is below 8 meters, so that's no good. But then after 2 p.m., here we are again. This whole section is perfect for canoeing. And then from 38 to 50 is also perfect. So we just have to turn these times into our AM, PM versions, and then we can write our statement. So that 14 hours means 2 p.m. because it's 2 hours past noon or 12. And then 26 is 2 hours after 24. So this is 2 a.m. 38 from 24, that's 14 hours later. So that's 2 p.m. again. And 50 therefore would also be 2 a.m. So pretty much, if we look at our sketches here, then we know any time between 2 p.m. and 2 a.m. you can go canoeing. So therefore, you can canoe between 2 p.m. and 2 a.m. any day. And that's it for this scenario. And for this scenario specifically, because I gave you that 8 meters, which is the midline, you are able to just use your sketch. If, however, I had given you a point that was not your max, min, or midline, you would have to use the equation and actually solve. But we'll do that in another example. So let's move on. In summer, the sun sets later than it does in winter. The time of the sunset can be important information for some people, including parents, environmentalists, and filmmakers. The latest sunsets occur around June 21st, which is the 172nd day of the year, and the earliest ones occur around December 21st, which is the 355th day of the year. So that right there already gives you your max and your mins. So the sunset times in Newmarket on these dates in 2019 are given in the table. So we know that on the 172nd day, we have a maximum sunset time. And on the 355th day, we have a minimum. So right there, if we know the time from maximum to minimum, to get a full cycle would mean to go back to the maximum, but this is just half the period. So if I subtract 355 minus 172, I get 183. So 183 would be half the period. So I'll just make a note of that right now. 183 days equals half the period. Now, part A tells us to determine an equation for the time of the sunset in Newmarket on the nth day of the year. So let's go ahead and make a little sketch and write down this key information. So we know that the max is 21.08. We know that the min is 16.70. So what I want you to do here is just pause the video, figure out your amplitude, figure out your midline, figure out the full period, and then calculate your K value. Then I want you to come back and check your work with the video. So for your amplitude, you should be doing 21.08 minus 16.70 and then divide it all by 2. And hopefully you get 2.19. And for your midline, you should be adding your max and min, so 21.08 plus 16.7, all divided by 2, and you get 18.89 for the midline. Now we said that half the period was 183, so if we double that, we get 366 days as the full period, which means your K value should be 360 divided by 366. And this does not turn into a nice decimal, so don't write the decimal version, just reduce your fraction. And if you reduce your fraction, you should get 60 over 61. Now I have a lot of nice information here, but I do need a bit of a sketch to figure out if I want to use sine or cos, and to figure out what my phase shift should be before I tie it all together to create an equation. So I'm going to go ahead and create a little scale here. So we have the number of days for our x-axis and sunset time for our y-axis. We know the maximum, we know the minimum, and we know the midline. So we can just put those into our scale. So the minimum was 16.70, the midline we calculated to be 18.89, and the maximum 21.08. And then we know that the maximum occurs on day 172 and the minimum occurs on day 355. So I can just roughly plot those. Not very accurate, but just to get an idea. So here's the maximum, here's the minimum, and I know halfway between those would be my midline. So if I know that my period is 366, I can divide it by 4 to get those key point values. So when I do that, I get 91.5. So every key point occurs 91.5 days apart. So if I just add 91.5 to 172, I get 263.5. And then if I subtract 91.5 from 172, I get 80.5 for my next midline point. And if I subtract once more 91.5, I get negative 11. So we don't even reach the minimum at the beginning of the year. So here is my sketch, and I haven't actually touched the minimum just yet. And just for myself, I'll put that negative 11 there just so that I know when that other key point occurred. Now that I have a nice sketch, my scale is somewhat labeled to represent those key points, I can pick my starting point. And it's really up to you what you want to choose. I personally would probably just choose that maximum because that's the point that was actually given to me. You can technically pick this midline point as well, but if you messed up on that point and you put the wrong phase shift, it's going to mess you up for the rest of the part. So I'm just going to stick with that maximum, which means I have a positive cosine. So now let's write our let statements, and then we can set up our equation. So let S represent sunset time. Let T represent time in days. Okay, so we have S at T equals, we said it's a positive cos, so my amplitude of 2.19 is positive, cos. My K value is 60 over 61. And because I'm starting at that maximum, which occurs 172 days later, my phase shift is 172 to the right. So I'm going to write T minus 172. And then I can finish my equation off with my midline, which is positive 18.89. Now we can use this equation for part B and C. So for part B, it says calculate the time of the sunset on August 1st of 2019. So first thing we have to figure out is what day is August 1st. So if you think about the number of days in each month, you can calculate that. And if you'd like to give it a try, you can pause the video here and try to identify the day number. Otherwise, August 1st is day 213. So if I am given the day, or the time in this case, then I can plug it into my equation and then see what I get. That is exactly what I'm going to do. So using function notation, I'm replacing T with 213. So I'm doing S at 213 equals 2.19 cos of 60 over 61 times 213 subtract 172 plus 18.89. And now when you plug this into your calculator, you're going to plug it in exactly the way you wrote it with all of those brackets, because if you miss a bracket, it's going to give you the wrong answer. So I want you to pause the video here and plug this into your calculator to see if you get the same thing as I do. So hopefully you got 20.56. So now we can write, therefore, on August 1st, the sun sets at 20.56 hours. Okay, so this one, because I gave you the independent variable, which was the day, we can just plug it into our calculator. Now for part C, we're going to do the opposite. For C, I said determine the date or dates when the sun sets at 6 p.m. Now, first of all, we should notice that the sunset time is given to us in the 24-hour clock. So we have to figure out what 6 p.m. is in terms of that. So if we add on the 6 to 12, which is our noon, then we will get 12 plus 6, which is 18. So we're pretty much trying to figure out when our equation is equal to 18. Now in this scenario, we cannot just look at our little sketch. The sketch can give us a general idea. I mean, if I want 18, I'm somewhere just below my midline. So I know that that day should be a little less than 80.5 and a little more than 263.5. So I have an idea in my head on what that date will be, but to get the exact date, I am going to use my equation, and I'm going to set that sunset time equal to 18 and then solve the trig equation. It will be a little more complicated than the way we've done it in the past, but we have the skills to do it. So let's go ahead and do that. So 18 is equal to 2.19 cos 60 over 61 t minus 172 plus 18.89. Now this part here, that is pretty overwhelming. That is all representing the angle of cos. So momentarily, we're going to make our life a little easier, and we're going to replace that overwhelming part with just a theta. And it will come back, but we're going to do this just to make it a little easier for ourselves, and you'll see why in a bit. So I'm just going to say, let theta equal 60 over 61 t minus 172. And we'll have to remember this for later on. So I'm going to rewrite this as 18 equals 2.19 cos theta plus 18.89. Now notice our goal is to solve for theta, and we know how to solve for theta. We just have to take the cos inverse and think about our cast rule and our reference angle and all of that stuff from solving trig equations, which means the first thing I should do is try to isolate for cos theta, which involves us first bringing over 18.89, just like you would if this were a linear equation. So I'm going to subtract 18.89 from both sides, and when I do that, I'm left with negative 0.89 equals 2.19 cos theta. And now I'm really close. I've almost isolated for cos theta. I just have to divide both sides by 2.19. And when I do that, I get negative 0.4064. And now this should look super familiar. Now, I notice that we have negative. And if I think about my cast rule, I know that cos is negative in the S quadrant and the T quadrant. So that means quadrant 2 and 3. So if I just figure out my reference angle alpha, I can make my modifications to get my two angles. And when I want to find alpha, we have to remember that we're always going to take, in this case, the cos inverse of the positive version of the number. And when we do that, we get approximately 66 degrees. And now, in quadrant 2, theta would be 180 subtract 66, which is 114. And in quadrant 3, theta would be 180 plus 66, which is 246 degrees. Now note that this is what theta is, but in our original equation, we never actually had theta, we had time. So now that we know what theta is, now we go back to that little let statement we made. Now we can replace theta with what it's actually equal to, so that way we bring back that time element into our equation. So now, instead of theta, I'm going to write 60 over 61 t minus 172 is equal to 114. And for our other angle, 60 over 61 t minus 172 is equal to 246. Now we're just going to isolate for our time. This is now just a linear equation. We already dealt with the trig part. So first thing we should do is get rid of that 60 over 61. And the way you can do that is multiplying both sides by the reciprocal or just dividing by that fraction. So I'm just going to show my work for this first one. I personally like jumping straight to the multiplying by the reciprocal. So when I do that, I'm left with t minus 172 on the left, and on the right, I'm left with 115.9. And now our final step is to just bring that 172 over by turning it into addition, and we get approximately 287.9, which we're just going to round to 288 days. And then I'll do the same thing on the right. So I'll multiply both sides by 61 over 60. And when I do that, I get 250.1. And then once again, bring the negative 172 over by turning into addition. And when we round, we're going to get 422. But we know 422 is way past a year. So if I want to bring it back into the 2019, then I should subtract a period. That way I'm back between that 0 and 365 day frame. So if I subtract 366, which is one period, I'm not subtracting 365 because that's not actually the period in this scenario based on the math we did before. But when we do that, we actually get 56. So on the 56th day and on the 288th day, the sun will set at 6 p.m. And you can check this work if you want. Take the 288 and replace t with it in that original equation. And take 56, replace t with it, and plug it into your calculator to see if you actually get 18 or close to 18. So now we can just write a quick therefore statement. Therefore, the sun sets at 6 p.m. on the 56th and 288th day. And if you wanted to, you could try to do the math and figure out the actual day of the year, but this is sufficient. All right, for the final example, the diameter of a car's tire is 54 centimeters. While the car is being driven, the tire picks up a nail. Draw a graph of the height of the nail above the ground in terms of the distance the car has traveled since the tire picked up the nail. So let's start off by drawing a little sketch. So I'm going to have height, and it will be in centimeters. So dealing with the height, I know that the tire has a diameter of 54 centimeters. And I know that the nail is picked up at ground level. And when it reaches its highest point, that would mean that the maximum is 54 centimeters. So we have a max of 54, a min of 0, and now we can figure out our amplitude and our midline. So my midline would be 0 plus 54 divided by 2, which is 27, and my amplitude would be 54 subtract 0 divided by 2, which is also 27. So I'm just going to mark these on my scale. 0, 27, and 54. Now the x-axis is a little different from other examples, and this is our distance traveled. And it will also be in centimeters. So for one full rotation of the tire, so the nail is picked up here at the bottom and it goes all the way around. That distance that it's traveling is the circumference of the wheel. And if we think back to our formulas from grade 9, circumference is equal to 2 pi r or pi times the diameter. Either one works because diameter is 2r, 2 times the radius. So if we can get our circumference and we know what one full rotation is, that would give us the period as well. So I'm going to go ahead and do that. The period is the circumference, which is pi times the diameter of 54. And I'm just going to round this to the nearest whole number to make it a little cleaner for us. And we get 170 centimeters for a full period. And just so that I know what I want to do with my scale, I'm going to take this 170 and I'm going to divide it by 4 for my key points. So 170 divided by 4 is 42.5. So I'm pretty much just going to go up by 42.5 on my scale, and I want to get maybe 2 rotations in. So we have 42.5 here. If we add another 42.5, we get to 85. Add another, we get to 127.5. Add another, and we get that 170, which is our period. So then we just have one more rotation to do. So let's add another 42.5 to get 212.5. Add another to get 255. And another 297.5. And then 340 for the end. Now that I have a nice scale and I know when every key point occurs, I can draw a sketch. So the nail is picked off at the ground, so at 0, 0, and then we go up to our midline, up to our maximum, midline, and minimum. And that's why I like to create my scale every quarter of the cycle so that I can sketch it nicely. And there we are. That is the height of the nail as the wheel turns. So now let's create an equation to represent this scenario as well. So since we have the period, let's also get our K value. So we're going to do 360 divided by 170, and I'm just going to simplify that to 36 over 17. And for my starting point, I'm definitely going to use the point at 0, 0. And that tells me that it's going to be a negative cos with no right-left movement. And it's a negative cos because we are starting at the minimum. So we do need some let statements here. So let H represent the height, and that's in centimeters. And let D represent the distance traveled, and that's also in centimeters. And now our equation will be H at D. We said it's a negative cos, so we're going to have negative, and our amplitude is 27, so negative 27 cos. Our K value is 36 over 17, and we don't have a right-left movement, so I can just put D and close the bracket, and now plus 27 for my midline. And now we can go on to part B. So for B, it says, how high above the ground will the nail be after the car has traveled 0.1 kilometers? So for part B, they are giving us the distance traveled, but our distance traveled is in centimeters on our scale, and they gave it to us in kilometers. So first thing I'm going to do, I'm going to turn those kilometers into meters and then the meters into centimeters just to make sure I don't mess up. So 0.1 kilometers, if I multiply that by 1,000, that's 100 meters. If I take the 100 meters and I multiply it by 100 for the centimeters, then that is 10,000 centimeters. So if I'm given the distance traveled, I can just replace D with 10,000 and then just plug that into my calculator. So that is what I will do for part B. So I am calculating h at 10,000. So why don't you pause the video and try to plug this into your calculator to make sure you plug it in correctly, and then come back to check your work. And I want you to round to 2 decimal places here. Okay, so hopefully you got 14.97 centimeters. And now we can write our therefore statement. Therefore, the nail is at a height of 14.97 centimeters. And now on to part C. So in C, it says, how far will the car have traveled when the nail reaches a height of 20 centimeters above the ground for the 5th time? So if I look at my sketch here, 20 centimeters is roughly maybe here. So this is the first time, the second time, the third time, the 4th time. So the 5th time is actually when we continue our cycle right over here. So I can have an idea of what that number will be, but I don't know exactly from my sketch. All I know is that it's greater than 340 centimeters. So I'm going to use my equation and set it equal to 20 and solve for my distance. And then I'll look at my sketch to figure out when that actual 5th time is. So 20 is equal to negative 27 cos 36 over 17d plus 27. And thinking back to the previous example, we don't like this part. So let's just say theta is equal to 36 over 17d, just to make it more familiar to us. So what we're really solving is the following. And we're going to isolate for that cos theta and use our cast rule to figure it out. So I want you to pause the video here, and I want you to isolate for cos theta, solve for theta in the 2 quadrants that match its ratio, and then come back to check your work. And if you want to try to complete it fully, once you've solved for theta, you can try to solve for d as well. So pause the video, try your best, and then come back to check your work. So first thing that you should have done is brought that 27 over and subtracted it from both sides. So that 20 minus 27 is negative 7. And then you can divide both sides by negative 27. And when you do that, you end up with a positive ratio. And we can just keep it as 7 over 27 equals cos theta. So thinking back to your cast rule, we know cos is positive in quadrant 1 and quadrant 4. So first thing, we do need to find our alpha. So alpha is going to be the cos inverse of 7 over 27, which is approximately 75 degrees. So in quadrant 1, theta is actually just 75 degrees. But in quadrant 4, theta is 360 subtract 75, which is 285 degrees. So hopefully you got 75 and 285 for your theta, because that part was a little more familiar from our solving trig equations. And now we just have to remember our equation doesn't have theta. It has the horizontal distance, or the distance traveled. So I have to replace theta with that 36 over 17d. So instead of theta equals 75, I have 36 over 17d equals 75, and 36 over 17d equals 285. And now we can either divide both sides by 36 over 17, or just multiply by the reciprocal, which is the same thing as dividing by that actual value. So when we do that, you end up with approximately 35.4 centimeters, and that's the first time. And for the second time, when you take 285 and multiply it by 17 over 36, you get approximately 134.6 centimeters. And that's the second time. Now, I'm going to go back to the sketch and label these points, and then we're going to problem solve on how to get the fifth time. So, the first time was at 35.4. and the second time was at 134.6. Now I know that the period is 170. So that 35.4, it occurs again a period later to be at 20. So if I just add my period, which is 170, I will get that next point. And when I add it, I get 205.4. And if I get 170, if I add 170 to 134.6, I can get that fourth time. But I don't care about the fourth time. I care about the fifth time. So if I take this 205.4 and add 170 again, then I've reached that point that I initially said would be the fifth time the nail reaches that height of 20 centimeters. So when I add 170 to 205.4, I get 375.4. And that is the fifth time when the nail reaches that height. So here the visual is super important. Your knowledge of solving a trig equation is important. And the idea that this cycle copy pastes over and over again, and your knowledge of the period is important to get to that fifth time. So now let's go ahead and write our therefore statement. Therefore, the fifth time the wheel is at a height of 20 centimeters is when the car traveled 375.4 centimeters. And there it is. So this is a very full example because you had to find an equation, you had to solve an equation in various ways, and use your sketch a little more. But like I said, once you can take the words and identify your max, mins, and your period and create that sketch, you're back to your regular trig knowledge. Create the equation from your sketch and then solve it if you need to. Just remember, when you are solving a trig equation, make that overwhelming angle part just equal to theta, and remember your knowledge of the cast rule and your reference angle. And that's it.